section 4.4, which we're going to do tomorrow anyway, which is important. And then there's one thing from chapter 11, which you won't see from until next semester, but this is just so you can do the first part of this AP problem. Because all the AP problems, when you get them, they have different parts. Sometimes they have integrals, which you won't learn until chapter 6, or the beginning of integral. And then there's stuff that you learn second semester. Some of it's mostly like derivatives, and then there's some integrals, but this one is mostly all derivative type stuff. So I thought it would be a good AP problem to do. But first thing that you gotta know, do you remember y equals e to the x? You guys remember that? Okay, that's called dx, the natural exponential function. Does anyone know where e to the x comes from? What it is? It's
like 2 point something.
Yeah, it's 2.71, I think, but it's the limit as x goes to infinity of 1 plus 1 over x raised to the x. So if you take bigger and bigger numbers and plug them in here, you end up getting this number e, which is about 2.718 something or something like that, okay? And that e is very important when you're talking about exponential growth, when you're talking about, like bacteria growth, banking, when you're compounding interest instantaneously and all that kind of stuff. But it comes up a lot in science, in math, and in financial stuff, and all kinds of places. So anyway, so what if I wanted to take dy dx of e to the x? Well, I just want to explore that with my calculator a little bit. And so you can do this. So I'm going to get my graphing calculator. Don't look yet. Don't look at my calculator. Don't look at the picture, because I think I already did this. But clear. So if I go y equals clear. Oh, I was in parametric mode. So I'm going to go back to function mode. And I'm going to plug into y equals clear. And so the e key is right above the natural log key. And we'll talk about some properties of logarithms to review tomorrow. And the reason it's right about the natural log key is because they're inverses of each other. Remember that? Okay? Remember that natural log and e, they undo each other? That's on that. Some of you took that quiz. You didn't know how to undo natural log of x. So anyway, if I hit graph, I should see something like that. Looks kind of like that. If I go zoom 6 and give me a normal viewing window and get rid of my stat plot that's there, I get something that looks like that. Now watch. You can take the derivative of that. So let's go back to the y equals, and we're going to take the numerical derivative, meaning that's a whole bunch of symmetric difference quotients. Remember you had that question on your test? Added up or plotted together. And so I'm going to go math 8 numerical derivative of bars, y bars, function y1, and comma x. That means with respect to x, comma x, for all values of x in the domain. And if I hit graph, it's graphing right now, but nothing's happening. How come? How come nothing's happening? What? It's broken. Well, let's go back to here. So what I'm going to do, I'm going to come back to this function. I'm going to turn off e to the x, and I'm going to leave on the numerical derivative of e to the x. Okay, so I can turn that off by clicking on the blinking light. Then I hit graph, and now I'm going to look at the numerical derivative of e to the x. There, it's graphing.
Holy crap.
What does the numerical derivative of e to the x looks like?
E to the X.
E to the x. Okay, and that's that's a unique function because we kind of talked, oh, look, it's the same. Someone was saying that today. So with e to the x, if this is y equals e to the x, and say there's a point on here. So one point on here would be 1 comma e, right? 1 comma e, 1. If I plug in 1 in here, I get out 2.7. Right exactly at that point, the slope of that curve is also, so if this is 1e, the slope of this curve is also e. See? And at any point on that curve, if I were to plug in like 2, okay, the slope at 2 of e would be also be e to the 2, right? So for that curve would be e to the 2. And then if I plot all those slopes, I get exactly the same thing as the curve. So, and there's a proof of that in your book if you're interested in why that's true. But yeah, so as long as you know that y equals e to the x, the derivative of that is equal to e to the x. Okay? So, so then it follows the chain rule also works. If you have something like dx of e to the u, that is equal to e to the u times du dx. You understand what I mean? That means the chain rule applies. Right? Are you focusing, Joel? So,
But you don't take away one.
so if I were to have e to the 2x squared plus 7, and I want to take the derivative of that, it is just what? E to the 2x squared plus 7 times something. Times 4x. That's all. Okay? So you take the derivative of, you leave it alone, and then you take the derivative of whatever the x function is. Alright? So I'm going to give you an AP problem now. And this is what they look like. They're very exciting. And this is from a real AP test. And what I should have done is left specifically which problem it was, because then you might have been able to research it on the internet. What? It's okay. But don't look it up somewhere. Just,
What if we can't figure it out?
well, try. All I'm asking you to do on this is to try. Okay? It is an assignment. I want to see that you've attempted to do some of the derivatives and stuff like that. Okay? But, so, the first question, first of all, this is a parametric function. I'll do the first one with you. X of t equals 2e, what does that say? I can't read that. 2e to the 3t plus e to the negative 7t, e to the negative 7t, right? So what would be x prime of t, or dx dt? What would be dx dt, based on what I just told you? 2e to the 3t times 3 plus, hello, e to the negative 7t times negative 7. Okay, and you can simplify that to 6e to the 3t, 6e to the 3t minus 7e to the 7t. So that's dx dt.
Wait, is it to the negative 17?
To the negative 17, sorry. Okay? So then I'm going to let you find dy dt. I'm going to let you find dy dx. And they talked about this. So the thing that we haven't talked about is question A. Now what's weird is we've done everything B, C, and D, so you should be able to do those with the things I taught you. Because you know how to find the derivative of a parametric equation. But the velocity vector and the speed, these are two things that come up in chapter 11. The velocity vector is just dx dt, comma, dy dt. That's all they mean by the velocity vector. That gives you how fast it's going in a certain direction. And then the magnitude of that is the speed, okay? So the speed is what do you remember how you take the magnitude of something? Yeah, you take the square of the square root. So in that case, you're going to evaluate it at a particular point. I think it is at 0. Is that what they say? No, or at 0? At 0? Yeah. At t equals 0. So you're going to evaluate dx dt at 0 and square it plus dy dt at 0. And then you're going to square it, okay? And that's will give you the speed, because this gives you the velocity. So maybe one's going, x is doing this and y is doing that. So the speed is the square root of the square of the velocity vector, okay? And so we've done stuff like that before in pre-calc, I think. Except you didn't know, we didn't take the derivative. They just gave you a function. You had to find the magnitude of that xy function. Remember doing that? Should have. Okay. So anyway, that should give. So this is kind of for part A. Part B, I think you could do. It's just finding dy dx, which should be relatively simple. C, you have to find out where you have horizontal asymptotes, and D, you have to figure out where it's undefined or where you have vertical, it's not horizontal tangent lines, and D, you have to find out where you have vertical. So that's it, and that will also give you a preview of what we're going to learn tomorrow. Okay? Okay. Yeah.